instruction. And for any command language that we have well enough defined syntax that we can determine what are the keywords, what are user inputs, what are data fields, and do that transformation.
I have just one question. Now, this is very interesting. How this entire approach may work when you have a web services, which can be dynamically so my question is how this entire approach would work when you have web services which can be dynamically composed. So can you always trace back the creation of this?
Well, at some point the web service is going to be constructed from some code.
Right.
It might be composed, higher level service might be composed of many smaller services. But as long as any of those particular services that talk to a database, we can take that piece of the larger distributed application, analyze it, and transform just that one component. Then we'll be able to defend, because if that's the only one that talks to the database, we've also protected everything else.
But what about doing this flow analysis? Can the flow analysis be limited to just that piece of code, or has it to go and look at other pieces of code?
Well, at the moment, all we do is, given a particular set of class files, compiled Java, to find what are, it just goes through, finds all the standard Java database calls, the JDBC API, finds each of those calls in just that piece of code, and then traces back within that code to how the query was constructed. We don't have anything that traces across services.
Exactly, so that was my question. So that.
Okay. So that's command injection. We also wanted to deal with more generic memory errors in like C, C++ kinds of programs, compiled native binary code. So one particular type of attack we were interested in, which hasn't gotten a lot of coverage in the literature, this idea of a pure data injection. So if you recall from earlier, the code injecting buffer overflow, the goal of that attack was to overwrite the return address of a function so that it jumped back to the injected code. But what if the goal of the attacker was only to overwrite the contents of those two local variables, x and y, that happen to be in the way? You can see this in a case if the function was doing some kind of security critical check, checking privileges, checking a user ID or password kind of thing. If you can overwrite just one of those variables in such a way that it alters the outcome of that function in a security relevant way, you can compromise the program in a way that a code injection defense that's only looking at the return address will never notice. So there's one good example of this in the literature a couple of years ago at Usenix. A paper was published about an attack that made use of a fairly old vulnerability in an FTP server that was originally a code injection. Use that same vulnerability to do a data injection, overwrite the effective user ID of that session. So instead of user whatever, it overwrites that user ID with 0 and becomes root on the machine, using the same vulnerability. So the way we've tried to deal with this, there's many different types of vulnerabilities that can lead to this kind of data injection. First, we had to try and categorize what are all those, and can we actually come up with defenses against them. So obviously buffer overflows are a big one. Another problem is uninitialized reads to memory. So if the contents of the stack don't get erased between function calls, some set of functions calls down, leaves all data on the stack, goes back up the stack, goes to further through the code to another function call, ends up using some portion of the stack. If one of the variables of that function isn't properly initialized before the value of some variable is used, an attacker might be able to alter the contents of that structure, control how the program goes on. Format string attacks, like a printf format string. It's something like, it's Well, it's kind of a bounds checking problem, except it's on the bounds checking the number of arguments to a function. So in certain cases, one of these attacks can lead to almost arbitrary random read-write I/O to the whole process memory space. So clearly we needed to deal with that one by bounds checking how the arguments get put into various types of functions. Then there's a whole wide range of heap-related errors, dangling pointers, double free kinds of things that can lead to alteration of data on the application heap. So for each of these different types of vulnerability, we've tried to come up with a different style of defending against that and a way of injecting that defense into an existing program. So just jump through them. Find my mouse again. So as far as buffer overflows, well, the general way we defend against this is analyze the program, try to figure out, based on the code and how it executes, where buffers are in memory, what are the boundaries of those buffers, and then we try to insert checking code around any access to that buffer. So there's many different ways we can do this inference to figure out what parts of memory are buffers. We can watch as variables are read and written to as the code executes in a dynamic code translation environment. We can look at particular snippets of code, and based on certain heuristics, we can identify that this looks like a loop body that iterates across some kind of buffer. And we can identify what that some piece of memory is a buffer and what its bounds likely are. And general other types of data that might be there, debug symbols, anything else we can make use of in this analysis. So there's definite limits to what we can do with static analysis of a program in a binary case, especially with x86 instruction set. It's very difficult even to know if your disassembly of the code back into x86 assembly is correct, as instructions are variable length. You're not always sure where a function actually begins and ends. So what we've had to do is do a lot of dynamic runtime observation and analysis of the code. So our example here is some function, a couple of simple functions, do some math and multiplication. On the right is the x86 code that this function compiles down into. So based on this code, we can draw a lot of inferences, and also even more by watching it execute. So as the function goes through, pushes base pointer of the stack frame onto the stack, copies that to the stack pointer, allocates the local variable space for the function as an offset from the stack pointer. So now it moves the value 1 into some position of the stack. So now we know that that particular word of memory corresponds to an integer value, and we can use that later on. So at this point, then we can also trace that value back as it goes through registers again. So now we know that what the contents of the EAX register is, how that gets moved into another variable on the stack. See that the other function, the multiply function, is called. We know from the calling convention that how arguments are placed onto the stack, how the return value of a function comes back from a function call. So then when the top level function moves that value back into another one, we'll now also know that that third position is also an integer value. And then the standard semantics of other stack-related functions let us know how the rest of the stack is modified based on leaving the function the standard calling convention prologue.